Hello everybody. Today we'll continue with our next numerical of slope deflection method. This will be our numerical, that is continuous beam ABC whose support A is fixed, and at point B and C we are taking a roller support over here. Okay. The loading in this numerical is same as your previous numerical, only support conditions I have changed, and one more portion I have added in that is portion CD, that is overhang one. Okay, and a load of 10 kN is acting at 1.2 meter distance. What is our claim? We have to analyze this numerical using slope deflection method, but condition is given to that if support B sinks by 2 mm, that is support B is sinking downward by 2 mm, and EI value is provided to, that is 16,000 kilonewton meter square. Okay, so due to this 2 mm sinking support, your translational conditions are going to introduce in this numerical. So how that conditions we have to take, that we'll see in this numerical. Okay, so we'll proceed with our first step, that is step number 1. We need to calculate the kinematic indeterminacy for this complete beam over there. Okay, so seeing at the support conditions, at support A you are having fixed support, so here decay value will remain 0, while at point B and point C you are having simple supports over there. Okay, so simple support, those are incapable support which introduces a kinematic indeterminacy. So one decay at point B and one decay at point C, so total decay value that comes equal to 2, and which are those values? That is theta B, suppose I am assuming those as clockwise rotation, and secondly that is theta C. So these two will be called as your unknown displacements. Okay, so our basic aim will be what? We have to find out the values of theta B and theta C further. Okay, so decay value we are getting total equal to 2. Then we'll prove, we have moved to step number 2. Okay, step number 2 is what? We have to calculate the fixed end moments over there. Okay, how we calculate fixed end moments? Considering all joints as the fixed one. So first we'll see, that is span AB. Okay, so in span AB, assuming that support A is fixed and support B is also fixed, we'll get fixed end moment for your first member, that is MF AB. Okay, in this complete span your UDL is loaded, so how much will be your fixed end moment? That will come equal to WL square divided by 12, and restoring moment sign we consider over here, so that comes here negative. Substituting the values of W equal to 10 and length of member AB is 4, you will get as minus 13.33 kilonewton meter. Your fixed moment values will remain same as your previous numerical. Okay, then second fixed moment will be your MFBA, that is same again, WL square upon 12, only restoring sign will get changed, that is it will come with positive, so you will get this as plus 13.33 kilonewton meter, right? Then in next span, that is span BC, so next fixed moment will be your MFBC. MFBC, point load acting at non-uniform distance, so that will be equal to minus WAB square divided by L square, where A is your 4 meter and B is your equal to 2 meter over here. So if you calculate this will get equal to minus 5.33 kilonewton meter. And last MFCB, so that will get plus WA square B divided by L square, so that will get as plus 5.33 kilonewton meter. Your fixed moment values are same as your previous numerical because your loading is same over there. Okay, then in addition to this fixed moment, we'll consider this overhang portion CD over there, but for this portion we do not consider the fixed moment over there. Okay, because fixed moment is considered between support to support conditions, but here at point D there is no support over here, so your fixed moment will not be considered. Instead, in this portion CD, due to this 10 kilonewton load over there, this will introduce a moment at point C over there. Okay, that is it will form a moment at point C, so we'll find out that moment over there, so that is, I will call it as additional moment, that I will call it as additional moment, and that will be for M CD over there. Okay, so that moment will be how much? That is equal to load multiplied by its lever arm, that is 1.2. So that comes equal to 10 multiplied by 1.2. So this comes equal to 12 kilonewton meter. This moment will not get changed throughout your numerical order. So this MCD, that will be your final moment that will go into calculating your last step, that will remain same. That is MCD is equal to 12 kilonewton meter. Okay. Here, whatever this additional moment we have got, that is MCD equal to 12 kilonewton meter. Okay, that will remain positive. Why? Because whatever this point load acting at over this overhang portion at point D is there, this will form a clockwise moment of 10 into 1.2 meter at this point C over there. Its restoring moment will be anti-clockwise nature, but actual nature of that moment will remain clockwise. So that is why we are while considering this additional moment MCD, that comes equal to plus 12 kilonewton meter. Okay? So you have to mark this point over here. Okay, so that is plus 12 kilonewton meter moment. Next, we'll move to our step number 3, that is slope deflection equations. Okay, so for first member we'll consider here, that is first member is your MAB. So basic equation for MAB is what? That is equal to MFAB plus 2EI upon L into bracket near end rotation, that we take 2 times of theta A plus theta B minus 3 times of delta divided by L. Here your delta value will not become 0 over there. Why? Because your sinking support condition is provided over. That is why a translation moment will be inducing over here. So we'll substitute the values over here. So MFAB that we have calculated, that we have got equal to minus 13.33. So minus 13.33 plus 2EI upon L. L will be your length of member AB you are having equal to 4 into bracket 2 times of theta A. Now theta A, here you are getting 0 because decay value for fixed support is always 0. Okay, so that will be your known displacement over there. Okay, so that theta A will become 0. What will remain? Theta B minus 3 delta upon L. Now this delta value that is provided to you, that is equal to 2 mm over there. But how we have to take this value over there, that we'll see first. Suppose this is your member AB and this is your next member, that is member BC. A translational displacement of 2 mm is provided at point B over there, which is sinking in downward over there. Okay, so in both this member I have marked this translational displacement as my 2 mm over there. So due to this sinking, what will happen? A translational rotations will be induced in this member AB and member BC also. Okay, so we'll mark those translational rotations over there. So in this member AB, your pattern will be in this way, which will be forming a translational rotations of anti-clockwise nature in member BC. Same way, in member AB, and in same way for member BC, you'll be having those translational rotations clockwise in nature over there. Now considering values of this value will come 6EI delta divided by L square. That is the same value we consider in this equation over there, and same way here you will get 6EI delta upon L square. These values will be at both the ends over there, 6EI delta upon L square, and here also you will get 6EI delta upon L square. Okay, now second concept for this, it is about this sign convention for this displacements over there. Okay, so we have seen in our second lecture over there how to take sign conventions for this 6A delta upon L square over there. So sign convention for this is opposite. If your moment is possessing clockwise in nature, so that moments you have to consider as negative over there, and if your moments are anti-clockwise in nature, so that will come positive in nature. Okay, so that is what you have to do for calculating this slope deflection equation for member AB and for BA. What you have to do, you have to consider this delta value here. This delta value you have to consider is as positive over there. That is, this delta will remain plus 2 mm. that is equal to plus 0.002 meters. Okay, or you can take 2 into 10 raised to minus 3 also. And same way this is for BC and CB. This delta value that will remain negative in nature, that is minus 0.002 meters over there. That is why while plotting this slope deflection equation, I have considered here plus or minus sign over there. Okay, so how we have to take that plus and minus sign, that is this concept over there. So if your translational rotation it is in anti-clockwise nature, then consider that sign as positive, and if it is in clockwise nature, then consider it as negative over there. So for AB and BA you will get delta positive, and for BC and CB you will get this delta negative. So we'll substitute this in your previous equation over there. So what will get this minus 13.33, right, plus 2 EI upon R, that is 2 by 4, I'll get equal to 0.5 times of EI, okay, into bracket theta B minus 3 into delta value, that is for member AB you are getting plus 0.002 divided by length of member AB, that is equal to 4. Okay, so we'll simplify this. What we'll get? Minus 13.33 plus, I'll multiply this 0.5 EI inside the bracket terms, so I'll get this as 0.5 EI into theta B minus 0.5 into EI value is given to, that is equal to 16,000, that I'll substitute over here, into 3 into 0.002 divided by 4. So if you simplify this, I'll get the final equation for my first member, that is MAB equal to minus 13.33 plus 0.5 EI of theta B minus, we'll simplify this term, that is I'll get equal to 0.5 into 16,000 into 3 into 0.002 divided by 4. So I'm getting that equal to 12. Further you can simplify this, that is MAB is equal to, you can simplify this, minus 13.33 minus 12, that I'll get equal to minus 25.33 plus 0.5 EI into theta B. So this will be my first slope deflection equation for your member AB, that is my 25 minus 25.33 plus 0.5 EI into theta B. Now we'll see for next member, that is MBA. Okay, so for MBA directly values I'll write, that is MFBA first. So MFBA I am getting plus 13.33 plus 2 EI upon L, that will remain same, so that I'll get as 0.5 times of EI into bracket near end rotation, that will be theta A, but it will remain 0 due to your fixed support condition. So what will remain here? 2 times of theta B minus 3 delta upon L. Now 3 delta upon L, for BA member also you have to take this as positive. So whatever this value you have got, that is equal to 12, that will remain same for your member BA also. Okay, so I'll write that over here, that is minus 3 into 0.002 divided by 4. Okay, so if you simplify this, what I'll get? Plus 13.33, this term you are going to get 0.5 EI into this total term that you are getting minus 12 over there. So 13.33 plus 0.5 into 2, that you will get EI into 1 theta B minus 12. Okay, so if you simplify this, I'll get MBA is equal to 13.33 minus 12, I'll get 1.33 plus EI into theta B. That will be my equation number 2. Okay, so 1.33 plus EI into theta B, that will be my equation number 2. Now we'll proceed for our next member, that is member MBC. MBC equation we'll see, that is equal to MFBC, that value we have got MFBC from this friction moment minus 5.33 plus 2 EI upon L. L of member BC is your 6, so 2 by 6, that becomes equal to 0.33 times of EI into your near end rotation, that will be your 2 times of theta b plus far end rotation theta c minus 3 delta divided by L. Okay, so we'll substitute delta value here, minus 5.33 plus 0.33 EI into bracket 2 theta b plus theta c minus, I multiply this 0.33 EI to this 3 delta upon L term, so that becomes 0.33 into EI values provided to, that is 16,000, okay, into 3 into, now delta value for member BC we have seen over here, for BC and for CB you have to substitute that delta value equal to negative 0.002, so I substitute that value over here, minus 0.002 divided by length of member BC, that is given to equal to 6. Okay, so simplifying this, I get minus 5.33 plus 0.33 times of EI into bracket 2 theta b plus theta c minus, I'll solve for this term over there, that I get 0.33 into 16,000 into 3 into minus 0.002 divided by 6, so I get this as minus 5.8, so that minus and this minus, that will become plus 5.28, you can simplify it with minus 5.33, so final equation for MBC you will get as minus 5.33 plus 5.28, that is almost 0 value you will get, so what will remain? Only 0.33 EI into bracket 2 theta b plus theta c, so that will be my equation number 3. Next equation, that is for MCB. Okay, MCB, that we have calculated MFCB, again it is plus 5.33 plus 2 EI upon L, that we get as 0.33 EI into bracket near end rotation, that will be theta b plus far end rotation will be 2 times of theta c minus 3 times of delta divided by L. Okay, so this I get as plus 5.33 plus 0.33 EI into bracket theta b plus 2 times of theta c. Okay, and this 3 delta upon L into 0.33 EI that we have calculated in our previous step, that I have got as plus 5.28. Okay, so simplifying this, what I get? MCB is equal to 5.33 plus 5.28, almost I get 10.61. Okay, that is 0.33 EI into theta b plus 2 times of theta c plus 10.61, that I get as equation number 4 over there. Sorry, here there is correction over here. Whatever value we have calculated for fixed moment MFCB, instead of this 5.33, this value comes plus 10.67. Okay, so here in substitution in slope deflection equation for CB, here instead of 5.33 that comes 10.67, here also that comes 10.67. so simplification of this 10.67 plus this 5.28, that we get equal to 15.95. so that we get 15.95. so note this correction over there, that is MCB you are getting 0.33 times of EI to theta b plus 2 times of theta c plus 15.95, that is equation number 4 over there. Please note this correction over there. Okay, now we will move to our next step, that is step number 4. All our equations are completed over here, so we will move to next step, that is step number 4, that is your conditions of equilibrium. Okay, for conditions of equilibrium, I have told you in the previous lecture that the value of dk equal to 2, that much number of conditions you have to consider in numerical order. That is, for solving these two unknowns, that is theta b and theta c, you will require two equations over there. That is, two conditions of equilibrium will emerge over there. So condition of equilibrium will see, suppose at point A, this support A, that is your capable support over there, so that can resist bending moment. So we cannot say that MAB will come 0, like as we have taken MAB equal to 0 in your previous numerical. So that condition will not arise at point B. At joint C, you can say, to keep this joint in equilibrium, whatever moment acting at point B, MBA and MBC shall come equal to 0 over there. So my first condition that comes, first condition at joint B. First conditions my comes at joint B over there. What is that? MBA plus MBC shall come equal to 0. Okay, so what you have to do, you have to substitute the equations of MBA and MBC over here. So equation of MBA, that is our equation number 2 here. I'll write that equation, 1.33 plus EI into theta B, plus equation of MBC, that is our equation number 3 over here. So I'll write that equation over here, 0.33 of EI into bracket 2 theta B plus theta C equal to 0. We'll simplify these conditions. So first we'll see for constant terms over here. There is no constant term over here, so what will remain? Only just 1.33. okay, when it goes on RHS side over here, so that becomes equal to minus 1.33. remaining now theta B and this bracket term over there, that you have to simplify. So from both these terms I take EI common over there. Okay, so what remains here? 1 theta B, and here 0.33 into 2 times of theta B. Okay, so this remains as theta B plus this will come equal to 0.33 into 2, that comes equal to 0.66 of theta B. Next theta C term is remaining, so 0.33 into theta C. So here I get my first equilibrium equation. What will be that? Theta B plus 0.6, sorry, here it is theta C, so 0.66 of theta, no, this is theta B itself, that is 1 theta B plus 0.66 theta B. I get 1.66 of theta B plus 0.33 times of theta C is equal to minus 1.33 divided by EI. So that will be my first equilibrium equation. I'll call it as A over there. Okay, then for second equilibrium equation, you have to consider the next joint over there, that is second equilibrium equation. Where it will be? It will be at joint C over there, that is at the incapable support. So here I write at second condition at joint C. Okay, at joint C, what will be that condition? MCB that shall come equal to MCB that shall come equal to minus 12 over there. Why? Because whatever this condition of overhang portion is coming, that is 10 into 1.2, it forms a moment over there, that is we have taken this additional moment over there. Okay, so restoring signs we have to consider, or instead of this you can write MCB plus 12 must come equal to 0 over there. MCB plus 12 that shall come equal to 0 over there. Okay, so we'll substitute the value of MCB over here. MCB, that is your equation number 4. We have got this 0.33 times of EI into bracket theta B plus 2 theta C plus 15.95 plus 12 is equal to 0 there. We'll simplify this. This becomes 15.95 plus 12, that becomes 27.95. Okay, when it goes on RHS side, that becomes minus 27.95 divided by EI. EI is what? That I have taken common from this term over there. This EI will get divided over there. So what will remain here? 0.33 times of theta B plus 0.33 into 2, that becomes 0.66 times of theta C is equal to minus 27.95 upon EI. That is my equilibrium equation number 2, or I'll call it as equilibrium equation number B. Okay. Okay, now for solving the values of theta b and theta c, we need to solve this equilibrium equation A and B simultaneously over here. So solving equation A and B, we get the values of theta b and theta c. If you solve these two equations over simultaneously, you'll get theta b is equal to 8.46 divided by EI and theta c equal to minus 46.57 divided by EI over there. So what was our basic aim? That to calculate the unknown displacement over there, that we have got as known displacement now, that is 8.46 upon E as your theta b and minus 46.57 upon EI as your theta c value over there. Okay, then we'll move to our last step, that is step number 5, to calculate the final moments over there. Okay, just simply what you have to do, you have to substitute this theta b and theta c values in your 4 slope deflection equations over there. That is equation number 1, equation number 2, and here we have got equation number 3 and 4 over there. If you substitute these values properly and simplify, you'll get MAB is equal to minus 21.1 kilonewton meter. Okay, then second value MBA you'll get equal to plus 9.79 kilonewton meter. Third value, that is MBC, you'll get equal to minus 9.79 kilonewton meter, and last value, that is MCB, you'll get equal to minus 12 kilonewton meter over there. So these will be your final moments, or you can call it as support moments over. Okay, now we'll verify our conditions of equilibrium from this. Our first condition is what? That is at joint B, MBA plus MBC must come equal to 0. Okay, so addition of these two, we'll check over here. MBA are getting plus 9.79 and BC are getting minus 9.79. So addition of both these, that will come equal to 0. So our first condition is getting satisfied. Same way, second condition we have taken at joint C, that is MCB shall come equal to minus 12, and the same value we are getting equal to minus 12 kilonewton meter. So our both the equilibrium conditions are getting completely satisfied over there. Okay, now using these final moments, we'll plot bending moment diagram by superposition over there. Okay, so for plotting bending moment diagram by superposition, first I take all the points over here, point A, B, C, and last point here it is my point D. You have to not leave the point D over there. In many times students what do, they leave this point D over there and just plot the diagram for ABC, so that becomes wrong over there. Okay, so these are my points A, B, C and D of your given beam over there. Okay, you have to consider this overhang portion also in this. Now as per your sign conventions, we consider this sign convention over there, that is if your member is considered moments coming at left hand side support, if those are negative we have to plot it on upward side, if those are positive those we are plotting on downward side over there, and we have to reverse this sign convention for your next end over there, that is on right hand side of your support. Okay, so for first member, that is member AB, you will be having MAB moment at your left hand side and MBA on the right hand side over there. So seeing MAB, you have got minus 21.1 over there, so that is negative, so it will be plotted on upward side over there. Okay, so that comes here 21.1. Next at point B you are having moment MBA, so that comes plus 9.79 plus it is, so again we are plotting it on upward side over here, so I'm plotting that over here, that is plus 9.79. Next, now we are switching to next member, that is BC member. Okay, so here whatever moment you will get, that will be your MBC, here you will get moment MCB. So we'll check MBC are getting minus 9.79, negativity, so plotted on upward side, already we have done that. Okay, and last, that is MCB, you are getting equal to minus 12 over there. So minus 12, what you have to do, that will get on downward side over there, so that comes here 12 kilonewton meter moment over here. Okay, so that comes here equal to 12. What you have to do, just join this moment points by a straight line over there. Okay, this is your point C here, right? And at point D, this moment will become 0. At the overhang portion, that moment will become completely 0 over there. Now whatever these moments are plotted, those are your support moments over there. We are plotting BMD by superposition, so span moment also we have to plot over there. Span moment are same as your previous numerical that we have got for AB equal to 20 kilonewton meter, and for BC we have got equal to 16 kilonewton meter over there. Okay, so 20 for UDL, that will follow a parabolic path over there. Somewhere below this 21 it will remain. Okay, so this will come equal to WL square divided by 8, that comes equal to 20, and for 16 that we are having at uniform point load, somewhere here that will come, that is equal to 16 kilonewton meter, and that is equal to WAB by L over there. Okay, this will be maximum under that point load position over there. And what you have to do, just shade this superimposed part over here. Okay, this part will not be shaded because it is not superimposed over there, so that will remain as it is. This diagram will be bending moment diagram by superposition. Okay, so in this numerical, two concepts we have seen: how to use the translational rotations if any sinking support condition is given to you, that you have to consider for this delta conditions over there in your slope deflection equation. And secondly, we have also seen how we have to solve the numerical for the overhang portion over there. What moment you have to consider. If this overhang portion is not considered over there, then what will get changed? The condition of equilibrium will get changed over here. That is this MCB, that will come equal to 0 as your previous numerical. But here overhang portion is given, so that is why that is adding a moment on this joint C. So that moment you have to consider under this equilibrium condition over there, and that will be highlighted in your throughout the numerical. That is moment of 12 will be acting at this joint C, which is seen in your bending moment diagram by superposition also. Okay, so hope so this lecture will be useful for you. Thank you.